welcome back to The Explainer. Today, we're focusing our lens on a truly radical approach to distributed system architecture. Think about the traditional relational databases you might have grown up with, systems like MySQL or PostgreSQL. In those classic setups, there's usually a very strict hierarchy. You've got a primary leader node that handles all the incoming writes, dictates the precise order of operations, and tells all the follower nodes exactly what to do. It's highly organized, but that organization comes with a massive, glaring vulnerability, the single point of failure. When that leader node crashes, everything just halts. The system has to detect the failure, scramble to elect a new leader, and redirect traffic. And that invariably causes downtime, user errors, and those dreaded late-night pager alerts. So today, we're throwing that entire centralized playbook right out the window. We're exploring a completely decentralized data architecture, one that removes the boss entirely and actually embraces a little bit of chaos to achieve almost unstoppable uptime.
Okay, let's dive into this, because it fundamentally challenges the traditional single leader model we're all so used to. Seriously, what actually happens if a database just abandons the concept of a leader entirely? Imagine a world where every single node in your database cluster is completely equal. There's no primary, no secondary, no active, no passive. In this kind of architecture, a client application can walk up to literally any database node and hand it a piece of new data to write. It kind of sounds like a recipe for total anarchy, right? I mean, if there's no central authority coordinating things, how do the nodes agree on what just happened? What happens if a server crashes right in the middle of a write operation? Or worse, what if two clients try to update the exact same record at the exact same millisecond on completely opposite sides of the cluster? How do you prevent your carefully structured data from turning into just a conflicting, contradictory mess?
To answer those questions, we need to define exactly what we're looking at. This architecture is formally known as leaderless replication. It's also really frequently referred to as Dynamo-style replication. And the reason for that is pretty interesting. While the core ideas were originally explored in older academic distributed systems papers, they became a massive, undeniable industry trend after Amazon published their famous 2007 white paper on their in-house Dynamo data store. See, Amazon was facing a massive scaling problem. They needed a shopping cart system that simply never went down, even if whole racks of servers lost power or network switches literally died. Think about the holiday rush. If a customer clicks add to cart and the database rejects the write because a leader node is busy failing over, Amazon instantly loses money. They needed a system optimized entirely for availability and accepting writes under absolutely any condition. This leaderless model spread like wildfire and inspired a whole generation of modern, highly resilient open-source data stores. Technologies you might actually be using right now in your own stacks, like React, Cassandra, and ScyllaDB.
All right, moving into our first major topic, the quorum equation, voting for the truth. So this brings us to the most pressing engineering question. If there is no boss node explicitly dictating the order of operations, and any node can accept a write at any given time, how on earth do we guarantee data accuracy? How do we know what the actual truth is when we go to read a record? Well, the answer lies in transforming database reads and writes into an election. And here is the formula that makes it all possible. This simple mathematical equation is the absolute golden rule of leaderless systems. W plus R must be strictly greater than N. Let's break those variables down real quick. W represents the number of nodes that must successfully acknowledge a write operation before the database tells the client it succeeded. R represents the number of nodes you must query during your read operation, and N is the total number of replicas designated to store that specific piece of data. The real beauty here is that developers get to choose these numbers. You configure them based on your application-specific needs, and as long as your write nodes plus your read nodes combined are strictly greater than your total replicas, you have successfully formed what we call a quorum. And this brilliantly illustrates exactly how that math plays out in practice. Let's say we have a total of 5 replicas storing a specific key, so our n equals 5. A client wants to write a new piece of data. The system is configured by the developer so that w equals 3. The write request gets sent out to all 5 nodes simultaneously. Now, maybe 2 of those nodes are currently offline, or busy undergoing maintenance, or just super slow to respond. It completely doesn't matter. As soon as any 3 replicas acknowledge the write, the system considers the write successful and lets the client move on. Now, imagine a client performing a read later on. The system requires R to equal 3, so the client sends parallel query requests and gets responses from 3 replicas. Because W plus R, which equals 6, is strictly greater than N, which is 5, the foundational math guarantees that the set of nodes we wrote to and the set of nodes we read from absolutely must overlap by at least one single node. Because that overlapping node was part of the rate quorum, it holds the newest, most up-to-date data. This means our read operation will definitely catch the latest update, even if the other responding replicas return older, stale values. The client just looks at the responses, compares the version numbers, and picks the newest one. As the source text states so perfectly, you can think of R and W as the minimum number of votes required for the read or write to be valid. You're essentially asking the cluster to vote on the state of the data. Typically, engineers will set these variables to a strict majority. So if you have 3 nodes in your cluster, you set both W and R to 2. If you have 5 nodes, you set them to 3. This democratic voting process is precisely what allows the database to natively tolerate node failures. If 1 or 2 nodes catch on fire, the system doesn't panic. It doesn't pause all traffic to hold some emergency election for a new leader because, well, there is no leader. As long as the cluster can gather enough votes to satisfy that quorum math, the application just keeps running smoothly. If a node votes no or simply times out because it's overwhelmed, the system just waits for a successful vote from one of the other healthy replicas to meet its quota. But of course, nothing is absolutely perfect. Let's look at when quorums fail, edge cases, and confusion. Before we go ahead and declare this the perfect database architecture, we really need a massive reality check. In the messy real world of distributed systems, even perfect math can't guarantee flawless consistency in absolutely all scenarios. Quorums give us eventual consistency, and that phrase is deliberately a bit vague. Let's rapid fire through some specific edge cases where quorums actually break down. First, consider what happens if a node crashes entirely, loses its disk, and gets restored from a stale backup. Suddenly, the number of replicas holding the newest data might secretly drop below your W value, completely breaking that overlapping math without the system even realizing it. Second, imagine you read a value while someone else is in the exact middle of writing it to the cluster. Some reads might hit nodes that haven't received the write yet, seeing the old value, while subsequent reads hit updated nodes and see the new one, creating a really confusing back and forth experience for the user. Third, if a write requires 3 nodes to succeed, hits 2, and then fails on the third, the database doesn't magically roll back those 2 successful writes. They just sit there on those disks, essentially half-written, potentially confusing future read quorums. Fourth, many systems use real-time clocks to resolve ties. If a server has a slightly fast clock due to a hardware quirk, it can silently overwrite or drop perfectly valid concurrent data because it incorrectly thinks its data is newer. And finally, concurrent writes can create sibling conflicts, which require special handling. The overarching takeaway here is that leaderless systems require incredibly careful engineering. You're trading simple, rigid consistency for raw availability, and you just have to accept that things will get a bit messy behind the scenes.
So why bother? That brings us to performance and resilience, the real world. Given all those terrifying edge cases we just covered, why would any engineer choose this complex architecture over a much simpler, highly consistent single leader setup? Well, it all comes down to the brutal realities of performance, resilience, and keeping your application online at all costs. Let's weigh the unique trade-off we make here. On the pro side, you get incredible high availability. There are literally 0 failover delays because there is no leader to fail. This means the system easily survives what we call gray failures. A gray failure is when a node isn't totally dead, but it's running incredibly slowly. Maybe it has a failing disk drive, a degraded network connection, or it's paused doing heavy garbage collection. In a single leader system, a gray failure brings the whole application to a crawl. But in a leaderless system? Now, what's really interesting about this slide is the concept of request hedging. Clients send the read request to multiple nodes in parallel, and they just take the fastest responses that form a quorum. The slow, struggling node is just entirely ignored. But on the con side, if you require 3 nodes to respond for a quorum, your read latency is ultimately bounded by the slowest of those 3 required nodes. And operationally, because writes are happening everywhere in no fixed order, it is extremely difficult to monitor replication lag and quantify just how eventual your consistency really is at any given second. And sometimes things fail so badly in production that you can't even form a proper quorum. Enter the sloppy quorum. This is a truly brilliant fallback configuration. Imagine a massive network partition separates your application server from the specific database nodes that normally hold its data. Instead of throwing a 500 error and dropping the customer's shopping cart update, a sloppy quorum allows the client to write that data to literally any reachable node in the entire database cluster, even if it's the completely wrong node for that specific piece of data. It prioritizes availability above all else. The system essentially says, hey, I'll hold on to this for now, just to save the data. This is paired with a mechanism called hinted handoff. That temporary node keeps a little note or hint attached to the data, almost like passing a sticky note to a coworker. Once the network partition heals and the correct nodes are reachable again, the temporary node automatically hands the data back to its rightful owners and deletes its local copy. It's an incredible safety net for write-heavy applications where dropping data is simply unacceptable. Next up, let's talk scale. Multi-region operations, spanning the globe. Now, let's zoom out.
What happens when we take this highly resilient, leaderless architecture and stretch it across the globe? Leaderless databases are exceptionally good at multi-region operations, spanning different data centers across completely different continents. Let's walk through how systems like Cassandra and CellGB handle this to avoid crushing the internet with redundant traffic. Sending data across underwater transatlantic cables is expensive and bounded by the physical speed of light, so we have to be smart. Step 1. Your client contacts a node in its local region. This node becomes the coordinator. Step 2. The coordinator blasts the write out to all the replicas within that local region so they get it instantly. But step 3 is the clever optimization. Instead of sending 3 or 4 redundant copies across a slow ocean cable to a data center in Europe, the coordinator forwards the write to just one single replica in that remote region. Step 4, that remote replica then takes on the job of forwarding the write to its local peers over the much faster local network. This dramatically reduces long-haul bandwidth costs and keeps latency way down. But this massive global scale forces developers to make a crucial choice for every single query in their application code. Do you want a local quorum or a global quorum? A local quorum only waits for votes from nodes in your specific data center. It's blazing fast and completely immune to cross-ocean network cables being severed. For example, if you're building a social media app and a user likes a photo, you'd use a local quorum because a few milliseconds of stale data is perfectly fine. But if a write happened in Europe a millisecond ago and you are reading in New York using a local quorum, you might read that stale data. A global quorum, on the other hand, requires votes from nodes across all geographic regions. It guarantees you get the absolute latest data, which is absolutely vital if, say, a user is updating their account password. But your application now has to wait for data packets to physically travel at the speed of light across the globe, adding hundreds of milliseconds of latency. It's the classic engineering trade-off between strict accuracy and raw speed. Which leads us to a fascinating challenge: detecting concurrent writes, the sibling problem. Let's look at the inevitable result of leaderless systems, what actually happens when 2 users write data at the exact same millisecond. Without a central leader to line them up in a neat little queue, we hit a collision. Imagine 2 clients interacting with the exact same shopping cart at the precise same moment. Client 1 adds flour to the cart, and almost simultaneously Client 2 adds eggs. They both send their writes to different database nodes. The database looks at these 2 incoming requests, examines their version numbers or vector clocks, and realizes they are completely concurrent. Neither write knows about the other. The database realizes it cannot safely decide which one is the true cart without risking data loss. So what does it do? Well, it absolutely doesn't drop the data. Instead, it saves both conflicting versions as siblings. When a client leader asks to read the cart, the database hands back both versions, one with flour, one with eggs, and basically says, "Here, you figure it out." The client application is then forced to logically merge these siblings together, often using specialized, mathematically sound data structures called CRDTs, conflict-free replicated data types, and then write the unified cart back to the database. This explicitly pushes the complexity of conflict resolution right up out of the database and straight into your application code. Let's wrap this all up. Summary and final verdict. We've covered a tremendous amount of ground here today, from quorum math to request hedging, the complexities of sibling conflicts, and global routing. Let's distill all these mechanics down into a final takeaway. So the crucial point is captured beautifully in this quote from the text. At its core, the resilience of a leaderless system comes from the fact that it doesn't distinguish between the normal case and the failure case. In a normal, traditional database, a failure is an emergency. It triggers alarms, automated failover scripts, and temporary downtime while a new leader is elected. In a leaderless database, failure is just Tuesday. The system is fundamentally designed to constantly route around slow nodes, merge conflicts on the fly, and rely on the raw mathematical overlap of quorums to heal itself. By purposefully sacrificing perfect, flawless consistency, we gain a profoundly resilient architecture that almost never suffers total downtime. And that leaves us with the ultimate architectural question. We've seen today that you simply cannot have it all. You have to choose your compromises. So where would you draw the line between flawless consistency and unstoppable availability in your next system design? Are you building a core banking application where every single penny must be perfectly synchronized across the globe? Or an e-commerce shopping cart where taking the user's order is the absolute highest priority, even if you have to computationally merge some conflicting items later on? It's all about picking the right tool for the job and deeply understanding the hidden costs of those tools. Thanks for joining me on this deep dive into leaderless replication, and I'll see you on the next explainer.